version of our International Inverse Problem Seminar. So we are happy to have a local today, Ruchi, which is a visiting assistant professor here at UC Irvine to give the talk. So he came to us from Virginia Polytechnic and State University, and he's now working on scientific computing, numerical analysis, and inverse problems. And in particular, he's been looking at the combination of deep techniques and direct sampling methods in various modalities. So thanks a lot, Ruchi, for giving a talk. We're looking forward to it. So the floor is yours.
Oh, thank you so much for the introduction, and thanks so much for the invitation to this very nice seminar. I think I need to I probably need to stop my video because because my internet is not very good. Okay. So in this talk, I'm going to discuss a deep direct sampling method for solving electrical impedance tomography and the diffuse optical tomography. And I think we have many experts here. You guys may be very familiar with this is two inverse problems. Okay. So this is joint work with Jiahua, and everything okay? I mean,
yes.
Okay. Sorry. Something. Okay. So this is a joint work with Jiahua, who is in the University of Birmingham, and Yi, who is a student of Jiahua. So we really want to talk with people from the community of inverse problems because we are looking for the experts' comments and opinions on this work. Okay. I think people here may be very familiar with this type. This is two types of inverse problems, but still, let me spend a little bit of time introducing these two techniques. EIT, it is known as Calderon's inverse conductivity problem. So the situation is if we have some inclusions buried in the object and we apply current and measure the resulting voltage and use this pairs of data for reconstruction of the inclusion. So it has the advantages of being low cost and radiation free. So it is really good for real-time reconstruction. People even call it 4D reconstruction, meaning 3 spatial dimension plus 1 temporal dimension. So for example, it can be used for monitoring, medical monitoring purpose. And nowadays, its applications are far beyond just medical imaging. It can be used for building sensors of robotics to make the robotics to sense what is touching it. This is really a hot topic these days. Well, so certainly this is applications demand really fast and high quality reconstruction. And in general, people describe how fast a thing is using the metawave blink of eye. Actually, I Google it, it takes like 0.1 second for one blink of eye. And I would like to mention that our algorithm can do a little bit better than this even. Okay. So we are also interested at the DOT, and this is a little bit deep. This is similar to the EIT. Instead of using the electrical data, they use it uses the optical data on the boundary to reconstruct the optical properties of medium inside that object. So there are also many applications about real-time DOT. This is two systems are built by our collaborator, Dr. William, from biological engineering. We are actually working with him to incorporate the experimental data into our algorithm. Okay. So this is two inverse problems are also known as inverse boundary value problem because the boundary only the boundary data are known, so they in general have very low spatial resolution. But we think the deep learning technique may have the potential to improve the spatial resolution. Okay. So, but in this talk, I'm going to focus on use the DIT as an example to describe our algorithm, and then I will present some results about DOT. So EIT is for EIT, this is the governing equation, and the coefficient sigma represents the conductivity values of the background median and the inclusion median. So if the coefficient is known, and this is a very simple PDE, and we can just use one of the boundary conditions to solve it. But now the case is the coefficient is unknown. Instead, we are given both of the boundary conditions, which is referred as Cauchy data pair. And we actually know multiple Cauchy data pairs in practice, and we need to use those data pairs for reconstruction of the coefficient. And I think you guys must be very familiar with the relation of the inverse problem to NTD mapping. If we know this mapping entirely, the entire mapping, we can apply it to any Neumann data and obtain the direct data. So basically, we know all the boundary data pairs. And in this case, the so-called the situational full data, the uniqueness can be established by many nice articles. But in our case, we assume there are only very limited Cauchy data pairs available, which are not sufficient to recover the to get a good approximation to the NTD mapping. So this is a little bit challenging because even the theoretical uniqueness may not be completely known. Okay, so traditionally, a very popular traditional type of methods is to use the iterative method for reconstruction. We construct a sequence of functions that is supposed to converge to the true coefficient. And this is done by minimizing the cost of function. This function or functional to be minimized in general measures the mismatch between the simulated data and the actual data. So then the key is the discretization of the quantity sigma to be recovered. So we can use finite element spaces for discretization because of the node regularity. In general, piecewise linear or piecewise even piecewise constant spaces are sufficient. And if in our case, if sigma is assumed to be a piecewise constant function, so inclusion has a constant value, the background has another conductivity value, which is still constant. So we can just discretize the interface, the inclusion interface, and we can use the shape optimization methods to identify the interface. So actually, I had one work with my PhD thesis advisor, Professor Towning, on this topic. We use the convolutional type functional for reconstruction, and we can see the numerical interface will approach the target interface eventually. But the problem is for this is iterative methods or the optimization type methods. In general, there needs a lot of iterations to converge. Especially the inclusion has a little bit complicated topology. The number of iterations could be tens of thousands, which is really expensive and not suitable for our purpose of real-time reconstruction. In contrast, another type of method, direct method, which are non-iterative in nature, and so that such that they are really suitable for real-time reconstruction. So different from the optimization method, the direct method look for some direct approximation to the indicator function of the inclusion, which is nothing but the characteristic function of the inclusion geometry. There are many works in this family. For example, like factorization method, which is one of the major motivation for this research, and also the very famous D-bar method, and which is based on the uniqueness proof, as well as other methods. All these methods are actually based on the, as far as I'm not really expert in the inverse problem theory, but I think all these methods are actually based on the very rigorous theoretical study of the inverse operator. So they in general have to assume the entire NTD mapping is known, which is not our case. we assume there are only limited Cauchy data pairs are available. So here we are particularly interested at the direct sampling method developed by Yaten Zhou, Professor Quadrupomito, and Professor Junzo. So you see their approximation to the indicator function is quite simple. F and G are the data functions, and F and G are the data function are the boundary data, and the eta is a function, is so-called popping function that only depends on the geometry of the entire domain, so of the whole domain. So we can consider it is known because it can be described by a simple PDE. And then we can just do some inner product and take some L2 norm to compute the index value. So this is one example I took from their article, and we see they can give a very reasonable reconstruction. Well, there are many works done to improve the accuracy, especially by incorporating multiple data pairs to improve the reconstruction quality. But these works are in general based on traditional mathematical derivation. So our idea is trying to learn this function, this index function, directly from data. But meanwhile, we try to mimic the mathematical structure and get the better neural network architecture. So this is our motivation. Well, before showing you the details, let me first convince you that deep learning is really, we think deep learning is really a good candidate for inverse problems, for computational inverse problems. So after literature review, we actually find that the methodology of the deep learning is really, very interestingly, it is really close to the methodology of computational inverse problems. First of all, they have the iterative methodology. So for scientific computing, for example, for solving PDEs, they use the neural network to represent the forward solution, which is the unknown quantity in this case. And then they just do optimization to fit the data and to determine those parameters in the neural network. And then the entire network is determined. And the solution is obtained. So for example, deep reads and deep clocking and the PIN physically inform the neural network. This guy is really popular these days by Professor George Kontakis. And so you see this methodology can be really naturally used for inverse problems because we only need to add some extra term in the reduce function to match the extra data to determine the quantity in inverse problems, because anyway, they have to solve an optimization problem. So actually many of these works have been applied to solve inverse problems. So nowadays, this approach is known as a function learning problem because at each instance, for each instance of data, they can only learn one function. When there is new data available, they have to redo after the optimization to get the new reconstruction. From from our perspective, we think actually the optimization problem in deep learning is not cheaper than the traditional method. So still, they are not suitable for our purpose, real-time reconstruction. In contrast, we actually find that there is a very interesting concept called end-to-end reconstruction. I think we have a question here, right? Oh, thank you for the reference. Yeah, thank you for that. End-to-end reconstruction, this is a very interesting concept because the idea of the end-to-end reconstruction still looking for the direct approximation to the operator that can map the data to the reconstructed imaging. So you see, the idea is really close to the direct methodology of the inverse problem. So but the difference is for traditional direct methodology, we in general use the traditional mathematical approach to to derive the approximation to the inverse operator. But for deep learning technique, using the deep learning technique, we use machine to learn the inverse operator directly from data. And in this case, there is no closed form. Instead, we use the neural network to represent, to express the operator, the inverse operator. So this is called nowadays, this is called the operator learning. And we think the operator learning really has the potential to combine the advantages of direct reconstruction approach and the optimization approach in a SenseNet. At the online stage, it can give very fast prediction because it only needs to do evaluation. So at this stage, when you use it, there is no optimization to solve. And the optimization is solved at the offline stage, which is and this is really expensive, but it's at the offline stage. So still can keep the accuracy, but without losing the efficiency. So if we combine them together, we think this has the potential lead to the real-time reconstruction. So this is our motivation for this research. Okay, so nowadays there are many, indeed there are many works for the new operator learning, especially for solving PDEs. For example, neural operator and DeepNet and the transformer. All this are different neural network architectures for scientific computing purpose. And for inverse problems, there are also many works, especially recently. Professor Yin actually proposed this some architecture to solve the EIT and the DOT. They actually assume the entire NTD mapping. NTD mapping is known, so they can build the neural network from the matrix approximation to the NTD mapping to the reconstructed images. And in our case, we only know limited Cauchy data pairs. So our idea is to use the mathematical structure of the DSM to design neural network. So let me show how we do this. Here we take this. Let's look at this so-called alternative format of the index function. So the center of the whole story is this function phi. Phi is a solution to the following elliptic boundary value problem. So F and G are the boundary data. So with F and G, we can just do and some surface Laplacian operator. But let's for simplicity just consider gamma is 0. So there is no such operator. So in this case, phi is nothing but some harmonic extension of the boundary data. And we can compute it and evaluate gradient at each point to get the index value. Well, this function phi seems to be really interesting from the perspective of deep learning because it can extend the boundary data to the domain interior. So originally we only have the boundary, the data on the boundary, so which there is no positional connection between the boundary data and the reconstructed image. But now we have the data on the entire domain. And by doing that, we can establish a very strong positional connection between the reconstruction and the input data. So that's a very interesting technique because this is really close to the so-called positional encoding in the technique of deep learning. So another thing, a very nice thing of the data function phi is that it can smooth out the noise on the boundary. So for example, the red curve is the exact data, and the blue one is the noise data. And if we compute their data functions, the zigzag behavior, the noised one only concentrates around the domain, and the inside domain we know that the PDE is very analytic, so they are actually very close to the exact data and also very smooth. And we think that's probably one of the reasons the neural network based on this function is really robust respect to very large noise. Okay, so let me show you our first trial. This is a feedforward neural network architecture. So the idea is very straightforward. So we just we just assume the index function at each point depends on the gradient of all those data functions at that point. And so if we put this entire input as a vector, so in another word, we need to find a mapping and can map each high dimensional data points into 0 and 1. So we basically need to classify all this as high dimensional data points according to their location. So it is basically a binary classification problem, and we all know that deep learning and algorithm is really good at classification. So this is the architecture of the neural network and feedforward architecture. So each neuron is it has a format like this, and the matrix W and the bias vector contains the so-called numbers, which are some parameters to be determined by data. And then we just input this vector into the into this neural network, and make it produce two values representing the probability of the point, which is inside or outside of the inclusion. And we need to evaluate such a high dimensional data vector at many sampling points inside the domain. So and also many inclusion samples. So this raises a question. So how can we obtain so many data? Actually, big data is one of the features of the inverse problem of the deep learning. Deep learning technique. So for inverse problems, we are actually lack of so many experimental data, because according to our collaborator, obtaining so many experimental data is very expensive. So instead, at this stage, we are trying to first train the neural network by synthetic data, and then adjust the resulting neural network by experimental data. But in this talk, let me just focus on the synthetic data. So we generate many inclusion samples by some simple geometric bodies, such as circles and ellipses, which are free to touch each other. And for each inclusion sample, we apply the current data, which are those trigonometric functions. And for each of them, we compute the corresponding voltage data. Just the direct boundary condition, and we combine them together to get the data function. So in this part, we solve this is two stages. We solve the forward problems, and we put the data functions, the 2D data functions, into the neural network for training. So this is their workflow, and this procedure is very expensive. But the good thing is it is only at the offline stage. So when you have a neural network which is well trained from this procedure, then you can just do evaluation. That part is really efficient, but this part is indeed expensive. So we apply the cross entropy as a loss function. We apply the cross entropy as a loss function, and we need to do the sample in both directions. One is the points to located, and another one is the inclusion sample, the geometry samples. We apply stochastic gradient in both directions to reduce the computational cost. And this is one example in the prediction. So the neural network, the algorithm can learn the inclusion near the boundary very fast, but learn the inclusion near the center quite a little bit slowly, because this is far away from the data. So this is for the prediction, not for the, this is for the training, not for the prediction. We will revisit this similar case when we do prediction. That's more interesting. Here I show you two examples for prediction, and we can see with multiple data pairs, indeed, we can obtain quite accurate reconstruction for 5 circles and for 4 ellipses, and it is really robust with respect to very large noise. But the problem is for simple, for the case of one single data pair, we couldn't obtain any reasonable reconstruction. This really shocks us because the original DSM can actually do a quite good job for a single measurement. So we actually test how many data pairs we need to recover this case of 3 circles. It turns out that we need 4 data pairs to do that. We are not really satisfied with this result. We actually have some technique to improve the reconstruction, but let me use this drawback of the algorithm as the motivation to show you our second approach based on convolutional neural network, which is a key of this research. And I'd like to pause it here. Any questions? Okay, no question. Okay, so let me continue. So it is based on a very different mathematical perspective. So for the original for the previous FNN architecture, we are looking for nonlinear mapping that can map the data at each point, which is to be located to its index 0 or 1. But of course, the value could be some number between 0 and 1, representing the probability. But now what we want to do is put the entire data function into some nonlinear mapping and make it produce the entire inclusion distribution. This is really an operator learning problem because the input functions and output functions are both input and output are both functions instead of just the vectors. They are functions. So now we should call it index functional, and the index functional depends on all this is input data functions v1 up to vn, and we use the convolutional network to represent this data function. We use the convolutional network to represent this nonlinear mapping because of this gradient. In the discretized level, gradient are computed by finite difference operators, which are nothing but the spatial case of convolutional operators with some spatial weights. So in another word, if we consider one layer of convolutional neural network, we can recover this operator. And if we make those parameters to be free, to be nullables determined by data, we expect this may give us a better operator with better approximation capability for this inverse problem. Okay, so there is so by doing that, we actually observe some very similar properties between our problems and the segmentation problem. For example, the point to be located is a pixel. And the data functions, phi are our data functions corresponding to image channels for segmentation. And the prediction, the inclusion distribution is the dense prediction for segmentation. But for segmentation problems, they are only, for each image, there are only 3 channels corresponding to 3 color features. But now our channel depends, the number of our, in our case, the number of channels depends on the number of given data pairs. For example, if there are n data pairs, we have n plus 2 channels. So the input is n plus is n1 and n2 are the spatial dimension, and n plus 2 are the number of channels. So it is a huge 3D matrix, and output is the 2D matrix representing the entire distribution. So which means this is indeed a little bit more complicated than segmentation. And this is only for the 2D reconstruction. For the 3D reconstruction, everything should be added by one. This is architecture of the convolutional network. And the one thing I want to mention is we have to add the extra 2 layers representing the coordinates of each point. This is due to the positional encoding, which is very important to make the neural network to work satisfactorily. Okay. So in this case, we just use the mean square error as a loss function and apply stochastic gradient to reduce the computational cost. This part is very standard, and this is the same case in the training procedure. So we can see we still have a similar phenomenon, but the neural network can learn the center inclusion a little bit better. Actually, that's only for training. For prediction, we can do much better. So for multiple measurement, multiple data pairs, we can indeed obtain a very accurate reconstruction, even with very large noise. But even for single measurement, the reconstruction is still very reasonable. It's almost accurate. There is a little bit roughing around the center, but overall, it is really satisfactory. So this already shows the CNN architecture indeed is much better than the FNN architecture, and we want to go back to understand why is that. So we go back to mathematics and we prove the following theorem. The theorem itself, well, its theorem itself is nothing because it just follows the original proof by Buha in 1999. But the result of this theorem is very interesting because the series determines the point of determines the location of each point looks like this. The majority part of this sequence, basically the location of the point depends on the convergence property of this series. And if we check the details of this of the mathematical structure here, this part indeed only depends on the gradient of data function at the given point to be located. But the coefficient here actually depends on the entire data functions. Those coefficients actually give the whole series more global structure. So that's why if we just use the data at one point, we may not capture the structure very well. So that explains why CNN works better. And this also from this research, we really enjoying that because we learned a very important lesson that math can really guide the design of neural networks. We have to add the right mathematical structure into the architecture of the neural network. Okay, so let's look at some more interesting tests. So in this case, we want to test the sensitivity of the algorithm with respect to the boundary data. So first we move this, we'll focus on this case of 5 circles, and we first move this circle to somewhere near the center, and then we completely remove this circle and obtain this this case of coefficient. We compute their corresponding boundary data, and we computed their corresponding boundary data, and we find that they are really close. They are really close to each other. So the relative difference is even less than 2% for high frequency data. This is much smaller than the noise level, so which makes the reconstruction quite challenging. But our algorithm can still get very interesting reconstruction, especially if there is no inclusion near the center, it clearly shows there is nothing near the center, and still robust with respect to large noise. And that's not the end of the story, because later on I'm going to show you we have some technique to reconstruct the center, to improve the reconstruction of the center inclusion or not. But we think this one is still quite satisfactory. Okay, so this case is very interesting because we find it by accident. So when we generate the training data, we fix the conductivity value to be 1 for the background median and 10 for the inclusion median. And then we generate the test data. We are supposed to generate the test data by using the same conductivity values. But once a time we made a mistake, we choose different conductivity values. But it turns out that the reconstruction cannot be affected very much by different conductivity values. So, for example, if this part has the conductivity 20 and this part have the conductivity 5 and this part has a conductivity 100, so you can see its reconstruction is cannot be affected by those different conductivity values almost as good as the original one. So so this is very interesting. This means that it has really good extrapolation property to different conductivity values. And this is also very useful in practice because when you generate the training data for the neural network, we don't have to choose very accurate. We don't need to know very accurate approximation to the conductivity values. We can only make a very rough approximation and still get very good prediction results when we use it. Okay, that's for, and this is the prediction for some different shapes, a triangle in the 2 bars and lunars. So because our neural network is only trained by circles and ellipses, so for those shapes, we cannot obtain very, very accurate reconstruction, but the overall shape is still okay. Especially this lunars, there is a hollow center and quite difficult to be recovered exactly. Well, if you want to have more accurate reconstruction, you can add those shapes into the training data set. And also we have some technique to improve it. Let me show you later on. Okay, so this is how we do this. So for all the previous results, we fix the order of the surface Laplacian to be 0. And if you look at the original DSM, they choose 1 for the fractional order for this surface Laplacian order. We originally choose it as 0 because we think this is nothing but a linear operator. Neural networks should be powerful enough to capture this linear operator, but it turns out that this may not be true. For the FNN approach, with a single measurement, we cannot obtain any reasonable reconstruction for 0 gamma. But if we choose some non-zero gamma, we have much more accurate reconstruction. This is very interesting. And especially this one for gamma to be 1, where the behavior is really close to the original DSM. So you see, even it's just a simple linear operator, if you do not tell this operator to your neural network, add this operator, add this kind of structure to the neural network, to the data, the neural network still cannot capture it. So which means some mathematical structure, if we already know, it's better to add it into the architecture. Okay, so that's for let's look at the CNN. So as I showed you before, if there is some inclusion near the center, the neural network cannot capture this center inclusion very well, especially its shape. But if we use non-zero gamma, the reconstruction of the center inclusion is much better. It's almost accurate, and also this lunars. It's if we use non-zero gamma, and its reconstruction is much more accurate, especially with multiple data pairs. But one issue is if there is noise, we find that using non-zero gamma is much more sensitive respect to noise than just using the original data. For example, 1% of the noise can totally have some obviously effect on the reconstruction. This is something we don't know yet how to address, but still, this is definitely an interesting direction to look at. Okay, so at the last series night, let me show you some results for DOT. Here we choose this model as a DOT, and I know the more accurate model should be a Robin boundary condition, but here for simplicity we just use a Neumann boundary condition. And for each we need to use the Cauchy data pairs to reconstruct the absorption coefficient mu, which is still assumed to be a piecewise constant. And this is the original index function. This is the original index function of DSM, and we compute their data functions by using the background absorption coefficient. And so everything is very similar to EIT. We just choose different data functions. Let me show you some results for 3D because the 2D is almost the same. So 3D is much more interesting. So we use the harmonic function to model the fountain on the surface of this object to be reconstructed. And we use 9 harmonic functions. So there are 9 data pairs. And we assume we can only obtain the data at very limited points. So not every point, just some limited points. And then we do use the data to do linear interpolation and use the linear interpolation as a boundary condition to compute the data functions V. So this is our approach. Okay, so the reconstruction is still very good. So you see, if we have 2 ellipsoids, the reconstruction is quite accurate and also very robust with respect to large noise. And we also try some different shape. For example, this dog. So you see, the overall shape is quite accurate, but here because we do not have that much memory, which we will talk about later on, we only use 2 ellipsoids to generate the training data set. So we cannot expect the neural network can capture the detail very accurately, but still the overall shape is quite satisfactory and also robust with respect to noise. And more importantly, as I mentioned at the very beginning, for one 3D reconstruction, the cost time is only 0.07 second, which is even less than the time for billion of eye. So this is really surprising us. Okay, so so this is pretty much I want to talk about. But at the next stage, next slide, I would like to summarize our story 9. So Java and I are both new to inverse problems. We are working on the traditional optimization algorithm previously. Nowadays, we try to adapt some techniques of deep learning, and we think something could be very, very interesting if we combine them together. So inverse problem, we have the classical algorithm that consists of the iterative methodology and the direct methodology. Direct methodology is to get some explicit approximation to the inverse operator. And we have, for inverse problem, we also have the deep learning algorithm, which consists of an operator learning technique and the function learning technique. Function learning technique is very similar to the iterative methodology based on purely solving the optimization problem to fit the data. But the operator learning is very different. They are using data to obtain the inverse operator itself. So what's really interesting to us is to combine the techniques from these 2 fields. For example, what we want to do is to because the current direct methodology for inverse problems already provides us with a very rich mathematical structure of the inverse operator. So for example, we want to add those mathematical structure into the designing of suitable, more suitable neural network architecture, and then use the operator learning technique to train the neural network to get the beta algorithm. So that's our purpose. But of course, this research is only at a very preliminary stage, and but we think this is an interesting direction to look at. And we also want to look for the experts comments, people like you. Okay, so there are many interesting works in the future. For example, currently we are incorporating 3D clinical data, experimental data into the training data set, and we try to compare the reconstruction with the software tools for DOT. And we are also investigating more suitable architecture for neural networks other than CNN. CNN, the problem of CNN is that it is indeed global, but if you really want to use CNN to capture the global architecture, you have to use a very deep CNN layers, and that will make the training much more difficult. So they are more advanced architecture nowadays, and we want to look at this direction. And we also one thing we are interested at. Another thing we are interested at is to reduce the memory cost. In the current situation, in the current case, for 3D reconstruction, we need at least 200 gigabytes memories to generate the training data set, because we need to extend the boundary data into the whole domain. That will cost much more memory than just using the boundary data, and that's indeed very expensive if you have a large number of samples. So this is something we are interested, and of course apply it to many other inverse problems. So this the talk is based on this is two references. One has been published in SysCon, and the other one is under review. And I would like to thank you for your patience. Thank you very much.
Thanks a lot, Ruchi, for the nice perspectives on the inverse problem. So we have time for some questions. So please unmute yourself and you can ask questions about this context. So any questions for Ruchi?
Yeah, actually, I have a question if no one else has a question, but I need to park first.
Well, in the meantime, Ruchi, could I ask you, so when you do the learning, so you should, in some sense, the method should be adaptive to the noise level. So do you actually, depending on the noise, do you incorporate that in the learning, or how is that?
Okay, so this is a very good question. So when we do the learning, when we generate the, let me go back to the CS slide. Yeah, here. So when we generate those training data, we do not add any noise. So they are pure, just based on the original data. We only add the noise when we do prediction. So we consult with people from biological engineering. So according to what they told us, it's really hard to know what's the exact noise in the practical situation. So that's why we choose this approach. There is no noise added in the training data, but a large noise added in the test data set for prediction.
Okay, and for the test data, how do you add the noise? Is sort of somehow additive, or how do you add the noise for the test data?
You mean? Sorry, I didn't get your question.
Yeah. So for the prediction, how do you add the noise?
Okay, at every point, that's like this. At every point, if this is the exact data, and we add the, for example, the Gaussian noise, or the uniform distribution, we test both many different cases of noise, and the noise is added point wisely.
Okay. Good. Yes.
Thank you for your talk. Just a quick high level question. My question is, your neural network architecture is somehow iteratively evolving, or is it fixed?
It's fixed. It's fixed. So we fixed the architecture, and we put the train data to determine those variables. So that's what we did. So it is not iteratively evolving, something like that.
Okay. Yes, so we still have time for questions. So if you have further things to be clarified, please unmute yourself, and you can ask Ruchi questions.
Hi, another just quick follow-up question.
Yeah.
Something, so it's direct sample, you take sample. My question is, if this is a valid question, say you sample, right? Sample 1, sample 2, sample 3. Do you think the architecture would depend on how you sample? Or
you mean sample? The samples you mean the inclusion sample, right? So the different shape of the inclusion. Is this what you mean? The different shape of the inclusion, or the sample at the point?
I was referring to sample data, the test data that you use to train.
Okay. Okay, so what our test data consists of many different inclusion samples. I think this is what you mean. And for those, we just fixed the architecture. We use a very large neural network at the very beginning. So because our sample number is more than like 10,000, so it's really for the 2D case, it's really a big data. So, and we just choose initially a very large, very deep network to handle this large this big data. So this is what we do, but it is fixed at the very first.
Thank you.
Thank you for your question.
So any other questions, Ruchi?
Yeah, I'm not really an expert in theoretical inverse problem, so.
But it's very nice to see it from the perspective of the learning here. That is so to see how the mathematical insight about the mathematical structure actually can guide you. So could you say one more word about this? How you mentioned this at the conclusion. So how the philosophy or approaches for incorporating the insight about the mathematical structure into the learning.
Oh yeah. So the key is that so originally, so this is I think I should go back to this slide. So originally we have the boundary data. We only have the boundary data, and we actually tested that if we only put the boundary data into a neural network, it is really difficult to train because you don't have the positional connection between your input and your output. Your output is the entire image on the domain, but your input is only the only the data on the boundary. If it's forward problem, that is okay because that's not that you post. But the inverse problem, this is a really a big issue for training. So, but the DSM, so you see, it constructs such a function very nicely that can extend the boundary data into the interior of the domain. So we find that this is really nice for building the neural network, just from those data functions to the reconstructed images. That's the foundation of the whole research. We hope this could get some attention from both community, from theoretical inverse problem and from deep learning community.
Yeah. Very nice. So if there are no further questions, let's thank Ruchi once again. And indeed, there are many interesting perspectives here, which probably we'll see further work in this direction in coming years. So thanks a lot for your talk, Ruchi.
Thank you.